March 1943. Detroit Arsenal Tank Plant. Major Leonard Fischer stands before a cross-section of armor plate split cleanly in two. The fracture surface shows a crystalline pattern that should not exist in properly forged steel. He is a metallurgical engineer, now responsible for ensuring that American tanks protect the men inside them. The plate came from a Sherman tank destroyed during testing in Arizona. The shell that hit it should have deflected. Instead, the armor shattered like glass. 3 crew positions directly behind the impact point would have been fatal zones. Fischer traces his finger along the fracture line. The steel failed not from the enemy's weapon, but from something introduced during its creation. American steel mills operate at unprecedented capacity. Furnaces that once produced structural beams now forge armor plate around the clock. The demand is absolute. Every week, the Army requires hundreds of tons of hardened steel for tank production. The mills push their equipment beyond peacetime limits. Smelting times are shortened. Cooling protocols are compressed. Quality inspections are accelerated to maintain output quotas. Fischer receives reports from 3 other testing facilities. Each describes similar failures. Armor plates that meet thickness specifications and hardness requirements nevertheless fracture under impact. The pattern is consistent across multiple steel suppliers. Something systematic is compromising the material during production. He arranges access to a steel mill in Gary, Indiana. The facility operates in 3 shifts without pause. Molten steel pours from blast furnaces into molds at temperatures exceeding 2,000 degrees. The noise is overwhelming. The heat turns the air into visible waves. Workers move between stations with practiced efficiency, aware that any delay affects tanks destined for combat. Fischer observes the smelting process. The steel contains trace amounts of moisture from scrap metal and alloying elements. At extreme temperatures, water molecules break apart. Hydrogen atoms, being the smallest elements, dissolve directly into the molten steel. Under normal production schedules, slow cooling allows these hydrogen atoms to migrate out of the solidifying metal. But wartime schedules do not permit slow cooling. The plates are removed from molds while still hot and moved immediately to hardening furnaces. The rapid transition traps hydrogen inside the steel matrix. The atoms gather at microscopic imperfections in the crystal structure, forming tiny voids. Individually, these hydrogen bubbles are invisible. Collectively, they create planes of weakness throughout the armor. When a shell strikes the plate, stress concentrates at these hidden voids. The metal cannot distribute the impact force. Instead of bending or deflecting the projectile, the armor fractures along the bubble-riddled planes. The result is catastrophic structural failure from what appears to be properly manufactured steel. Fischer returns to Detroit with samples from the Gary mill. He sections the plates and examines them under microscopic magnification. The hydrogen voids appear as dark spots scattered through the steel. Some samples contain hundreds of these defects per square inch. He calculates that approximately 15% of current armor production contains dangerous levels of hydrogen embrittlement. The solution seems obvious: slow the production process to allow proper degassing. But the numbers make this impossible. Reducing output by even 10% would mean hundreds fewer tanks per month. The invasion of Europe is being planned. The Pacific Campaign requires constant armor replacement. There is no slack in the production schedule. Fischer must find a method that identifies defective plates without slowing the manufacturing line, and ideally, a treatment that removes hydrogen without adding significant time to the process. He begins with detection. Standard metallurgical testing requires cutting samples from each plate and examining them under laboratory conditions. This is too slow and destroys the material being tested. He needs a non-destructive method that can evaluate entire plates in minutes. The answer comes from an unexpected source. Fischer remembers a technique used by railroad inspectors to check wheel integrity. They tap the wheel with a hammer and listen to the resulting tone. Flawed metal produces a different acoustic signature than sound metal. The principle is simple. Internal voids change how vibrations travel through steel. He acquires a set of precision tuning forks calibrated to specific frequencies. When struck against armor plate, a fork without hydrogen voids produces a clear, sustained tone. The sound waves travel through the homogeneous steel structure and reflect back in predictable patterns. But when the same fork strikes compromised plate, the tone becomes muted and irregular. The hydrogen bubbles scatter the sound waves, absorbing energy and creating acoustic dead zones. Fischer develops a testing protocol. Inspectors strike the tuning fork at 9 points across each armor plate in a grid pattern. They listen for tone clarity and duration. A trained ear can distinguish between acceptable resonance and the dampened sound of hydrogen-damaged steel. The entire test takes less than 3 minutes per plate. The challenge is training inspectors to recognize the difference. Fischer recruits workers with musical backgrounds, people whose ears are already trained to detect subtle variations in pitch and timbre. He creates a training program using known good and defective plates. Inspectors practice until they can reliably identify compromised armor in blind tests. By May 1943, acoustic testing stations are established at 3 major tank plants. Every armor plate receives tuning fork evaluation before installation. The inspectors work in quiet rooms isolated from factory noise, listening to the voice of the steel. The detection system immediately reveals the scale of the problem. In the first week, inspectors reject 240 plates. The rejected armor goes to a segregated area for further analysis. Fischer's laboratory testing confirms the acoustic method's accuracy. Plates that produce poor tones consistently show high hydrogen content under microscopic examination. But detection alone is insufficient. The rejected plates represent wasted production capacity and raw materials. Fischer needs a treatment that can salvage compromised steel. He returns to the fundamental chemistry. Hydrogen atoms are trapped in the steel because rapid cooling freezes them in place. If the plates are reheated to a specific temperature range, the hydrogen can diffuse out of the metal matrix without requiring complete resmelting. The process is called hydrogen bakeout. Fischer experiments with temperatures between 500 and 650 degrees Fahrenheit. At this range, the steel structure remains stable, but hydrogen atoms gain enough energy to migrate toward the surface and escape as gas. The critical variable is time. Too short and insufficient hydrogen is removed. Too long and production schedules are compromised. Fischer settles on a 12-hour bakeout cycle at 600 degrees. Rejected plates are placed in specialized furnaces overnight. The treatment adds 1 production day to the schedule, but it salvages armor that would otherwise be scrapped. The combined system of acoustic detection and hydrogen bay count goes into full operation in June 1943. Every plate is tested. Approximately 14% fail initial inspection. These plates enter the bakeout furnaces. After treatment, they are tested again. 92% now pass acoustic evaluation. The remaining 8%, which still show acoustic dampening after treatment, are rejected entirely and returned to the mills for resmelting. The impact on tank crew survival is immediate but difficult to quantify precisely. Armor that would have failed in combat is identified before installation. Crews receive protection that performs as designed under battlefield conditions. Fischer maintains detailed records. Between June and December 1943, acoustic testing evaluates 57,000 armor plates. 8,200 plates are rejected at initial testing. 7,500 undergo successful hydrogen bakeout treatment. 700 plates fail treatment and are scrapped. Field reports from North Africa and Italy show a decrease in catastrophic armor failures. Tank crews report that hits which previously might have caused complete structural failure now result in contained damage. The armor bends and cracks under extreme stress, but it does not shatter. This difference means survivable damage instead of crew casualties. The acoustic testing method spreads to other applications. Inspectors use tuning forks to evaluate welds on ship hulls, aircraft components, and artillery pieces. The principle remains the same. Sound reveals what eyes cannot see. Fischer receives a commendation from the Ordnance Department in January 1944. The citation notes his contribution to armor reliability and crew safety. He does not attend the ceremony. He is at a steel mill in Pennsylvania, training a new group of acoustic inspectors. By the time of the Normandy invasion in June 1944, every American tank rolling off production lines has passed acoustic testing. The armor-protecting crews at Omaha Beach and Utah Beach contains no hidden hydrogen voids. When German anti-tank rounds strike these plates, the steel performs as metallurgy predicts. It resists, deflects, or fails in controlled patterns. It does not shatter. Fischer's innovation operates in the invisible space between production and combat. His work prevents failures that would have occurred in circumstances where failure means death. The acoustic testing stations continue operation throughout the war, a quiet checkpoint where tuning forks sing the integrity of steel. The war ends. Tank production slows. The urgent pressure that created hydrogen embrittlement in the first place diminishes. Steel mills return to peacetime schedules with proper cooling protocols, but the acoustic testing method remains standard practice. It becomes part of the permanent quality control framework for armor production. Fischer returns to civilian metallurgy in 1946. He works for a company that manufactures pressure vessels and industrial boilers, applications where hidden material flaws can cause catastrophic failures. The tuning forks come with him. The principle he proved in wartime, that sound can reveal structural truth, finds application in peacetime industry. The 8,000 defective plates rejected by his system represent an absence. Tanks that did not fail, crews that did not die, families that received their soldiers home. This absence cannot be measured directly, but it exists as surely as the crystalline fracture patterns Fischer first examined in March 1943. The tuning forks still hang in the quality control office at the Detroit Arsenal, now a museum. They are simple tools, precisely calibrated steel bars that ring when struck. They represent a moment when the pressure of war nearly compromised the protection meant to preserve life, and when careful listening prevented that failure. Fischer's legacy is written in the tone of metal, in the sound of steel that holds true under stress, in the quiet certainty that what protects us has been tested by someone who understood what failure would mean.